Okay, so we're recording here. So, all right, before your Thanksgiving break, we talked about section 8.7, and section 8.7 was the section on Taylor and Maclaurin series. And what we learned was that if you have a function that is continuous and differentiable, meaning you can take multiple, take like an infinite number of derivatives of it, of the function. If the function's continuous and differentiable, then you can express the function as a power series. You can express the function over a power series for a certain interval of convergence. Okay, so a function is just like, you can't just say a function is equal to its power series for all values of x. But sometimes it is. Like if you look at, looking at this table, this again, in this table here is it comes from my handout, which is in your course content folder. Look under course content, find section 8.7, and you'll be able to download this handout that I made. But if you look at it, like for instance, the cosine of x, the Maclaurin series for the cosine of x equals the series n equals 0 to infinity times -1 to the nth power times x to the 2nth power divided by the quantity 2n factorial. That's true for an interval of convergence from -infinity to infinity, which means all real numbers. So what that means is for any value of x, you can express the cosine of x as you can express the cosine of x as an infinite power series for any value of x, because the interval of convergence is all real numbers. That's all x values. But like for instance, if you wanted to have the power series, if you wanted to express the arctangent, for instance, as its power series there, well, the interval of convergence is a closed interval from -1 to 1. So like you can express the arctangent of a half as a power series where you put in x equals a half in there, but you could use the power series for the arctangent of 3, because 3 falls outside the interval of convergence. So these Maclaurin series, we looked at how a few of them were derived in the last class, and basically deriving the Maclaurin series. Hold on here. Let me just deriving the Maclaurin series or Taylor series just comes from using the Taylor series formula. So the Taylor series formula is for any a value, any number. But if a equals 0, then the Taylor series becomes a Maclaurin series. Okay, so this is what we talked about before our like in our last class before Thanksgiving break. Is this helping? Is this reviewing helpful? Is this helping refresh your minds a little bit? Okay, are there any? Okay, thank you, Tina. Thank you, Mohammed. All right, thank you, Kahindi. All right, very good, very good. So, you know, in your homework for section 8.7, you'll have problems where you have to find the Maclaurin series or the Taylor series. And the functions in those problems wouldn't necessarily fall in this nice table here. But the table contains the most common functions that are used in mathematics. And that's why this table comes from your textbook, and that's why we have the table, so we can refer to the table. All right, but again, certainly you're going to see problems where you have to write a Taylor polynomial, a Taylor series or a Maclaurin series for a function that's not here in the table table, because we need to see that you understand how to find them Taylor or Maclaurin series. So on that note, what we do in section 8.8 is we talk about what are called Taylor polynomials. Okay, Taylor polynomials. All right, and I think, let's see here. What I'm doing is I'm just looking here at the textbook for a moment just to see. Yeah, I think what I'll do, let me just sort of go into the intro where the textbook is. One moment. Let me bring this up here. No, I don't want that. I want the ebooks. I just got to bring it up, class. Okay, one moment. Okay, let me stop sharing this and bring up the ebook. And obviously that's not the ebook. Hold on. Where is this? Here we go. Okay, so applications of Taylor polynomials. There are many applications of Taylor polynomials in math and physics, for instance. And so you all know what a polynomial is. You're probably, how many of you consider yourselves to be experts on polynomials at this point in your life? Wow, I thought I'd get some quick responses on that. Well, you've all seen polynomials. Okay. Esther says, Mohammed does, he says sadly no. But you know, you've all seen polynomials. Esther has, everybody has. Okay, so we're going to make a little connection here. Okay, so in this section, we explore two types of applications of Taylor polynomials. First, we look at how they are used to approximate functions. Computer scientists like them because polynomials are the simplest of functions. And then we can investigate how physicists and engineers use the Taylor polynomials in different fields like special relativity, optics, and so forth. Okay, so there are a lot of you know, applications, and actually in your web assigned homework for section 8.8, the third like problem where you look at an example deals with Einstein's theory of special relativity. Okay, don't worry, you'll be able to do it fine, but you don't worry about that now. Don't worry about that now. So, all right. So, you know, this is the, you know, Taylor series formula. And what they say here is, you know, so how many terms are in a Taylor series? So like if you look here at this Taylor series, f of x equals the Taylor series, how many terms are there in the Taylor series? So we're saying a function equals this power series. How many terms are in the power series? look at your summation. Your summation goes from n equals 0 to infinity. Okay, so that's right, Michael. There are an infinite number of terms in the series. Okay, so the function itself will actually equal the series itself. But we are going to approximate the function by taking a polynomial from the series. Okay, so like for instance, if you were to look at the nth partial sum of the series, okay, then you would have an nth degree Taylor polynomial. So you're taking the first n terms of the series. And we know that the more terms we take of the series, the better the series is going to approximate the function, because the function equals the Taylor series. It equals it. But if you take the first n terms of the Taylor series, you have a Taylor polynomial of nth degree, and it will approximate the function over a certain range of x values, and that's good. That's good. Okay, it'll approximate the function well over a certain range of x values. That's what the polynomial will do. So like for instance, the first degree Taylor polynomial is right here. F of a plus f prime of a times x minus a. That's a first degree Taylor polynomial. Okay. Second degree Taylor polynomial, you would add another term. You would have f double prime of a over 2 factorial times x minus a squared. That would be t sub 2. Okay. For t sub 3, you'd have to add the third degree term of the Taylor series. And so you can build up these Taylor polynomials as much as you want. And what they do in the intro here is they talk about the exponential function e to the x near 0, 1. So the Maclaurin series for e to the x is in your table, and you might want to download that table for the course content and maybe have it on your screen, so it's handy. But I guess I can see it's, well, yeah. If you look in that table, the Maclaurin series, okay, the second degree Taylor polynomial is going to be 1 plus x squared over 2. The third degree Taylor polynomial is going to be 1 plus x squared over 2 plus x cubed over 6. Okay, those are going to be them. Let me come back to this. Let me just hold on here, bring up the Blackboard here real quick. Okay, so what they're doing is, where are they getting these Taylor polynomials from? Well, here's the formula, right here. This is the Taylor series or Maclaurin series because they're a equals 0. This is the Maclaurin series for e to the x power. And they write out then the first 4 terms of that Maclaurin series. Well, the first degree Taylor polynomial would be 1 plus x. The second degree Taylor polynomial would be 1 plus x squared over 2, because 2 factorial equals 2. The third degree Maclaurin polynomial would be 1 plus x squared over 2 plus x cubed over 6. Okay, and you can keep going and going. Are there any questions on this? Are there any questions before we go back to the book? Or are you comfortable? Please let me know if you have any questions. Okay, who's comfortable so far? Maybe give me a thumbs up if you're comfortable. Okay, thank you, Michael. All right, Mohammed's comfortable. Thank you, Mohammed. All right, all right. So now let's go back to the book here. Okay, and what they do is they draw, in figure 1, they draw a picture of the exponential function e to the x. That's in red. And then they draw the first Maclaurin polynomials. Okay, T1, T2, and T3. Okay, they're Taylor polynomials about a equals 0. They use the abbreviate T because Taylor polynomial, but you're doing it about a equals 0, so they're really Maclaurin polynomials. And the values here give the values, hold on, let me make sure we're, yeah, okay, good. The values give a numerical demonstration. Well, I want to be careful. In the picture here, you have a geometric demonstration. Well, hold on, let me go up a little bit. Let me just put this in pink. This is really what I want to talk about. The graph of t sub 2 is that parabola. The graph of t sub 3 is that cubic curve, 1 plus x squared over 2 plus x cubed over 6. You can see t sub 3, the cubic curve, is a closer fit to the exponential curve than is the t sub 2 parabola. Okay? And that makes sense because the more terms you take of the Taylor series, the better the better the polynomial is going to approximate your function, and it'll do it over a wider range of x values. Okay, I mean, look at figure 1. Which Taylor polynomial does the best job in approximating e to the x power? Which polynomial clearly does the best job? Is it T1, T2, or T3? Clearly, T3. Clearly. And if you did the 4th degree Taylor polynomial, it would be even better. Okay, so this is the concept, the concept between or for section 8.8, and you know, they have a little table here where they show, like at x equals 0.2, they have, let me just kind of highlight the table here. At x equals 0.2, they compare the 2nd degree Taylor polynomial, t sub 2, its value, well, no, what they do is here's when x equals 0.2, okay. Man, I didn't want to change all of that, but hold on, we'll do that in yellow. When x equals 0.2, here's e to the x at the bottom. So e to the x, the value of e to the 0.2 is 1.221403. What they do is they evaluate the 2nd, 4th, 6th, and 8th, and 10th degree Taylor polynomials at x equals 0.2, and clearly, what does the best job? Well, the 10th degree Taylor polynomial, it actually does an equal job to the 8th and the 6th degree Taylor polynomial. But that's at when x equals 0.2. Look at when x equals 3. When x equals 3, e to the 3rd power is equal to 20.085537. Well, which polynomial, T2, T4, T6, T8, or T10, which polynomial does the best job in approximating e to the 3rd power? Okay, Michael says the 10th degree Taylor polynomial. Who agrees with Michael? Does anyone disagree? So I'd like a little more, I need a little more please, you know, a little more feedback. Thank you, Candy. I know, you know, it's kind of, it's, thank you, Alan. I feel focused if, all right, so let me ask you this. Let me ask you this. At x equals 0.2, the 6th degree Taylor polynomial, 8th degree Taylor polynomial, and 10th degree Taylor polynomial all approximated e to the third power very nicely. But when x equals 3, it's only, well, at x equals 3, there's a difference. The 8th degree polynomial t sub 8 does a better job than t sub 6. The 10th degree Taylor polynomial t sub 10 does a better job than the 8th degree Taylor polynomial t sub 8. The polynomials don't do quite as well. And notice too, even the 10th degree Taylor polynomial when x equals 3, 10th degree Taylor polynomial is 20.079665. E to the third power is 20.085537. So why do you think when x is 3, why do the polynomials not do as good a job of approximating e to the third power as they did when they approximated e to the 0.2 power? Why do the Taylor polynomials seem to not do quite as good a job? I mean, it's not bad, but why is that? Well, e to the x moves faster, Michael. That's actually a very good point. As you move away from x equals 0, the exponential function increases rapidly. Okay, is there any other reason? Well, look at the little comment here above. Okay, when in fact, the farther, well, there's actually, hold on here, let me, this is the key here. The polynomials here, T2, T4, T6, T8, and T10, are polynomials centered about a equals 0. But the farther x is away from 0, the more slowly the Taylor polynomial will converge to e to the x power. In other words, the Taylor polynomials will not approximate e to the x as well. The further away x is, the further away the value is from 0, a equals 0, the further away the x value is from a equals 0, the worse the approximation is going to get, typically. And that's true here. The approximations when x equals 3 for these Taylor polynomials are not nearly as good as the approximations for the Taylor polynomials when x equals 0.2. Okay, and so this brings up the question then, okay, how large should, you know, well, first of all, and I'll highlight this in yellow, when using a polynomial to approximate a function, we have to ask how good is the polynomial approximation? How large should we take in order to achieve desired accuracy? In other words, what should the degree be of our polynomial to get a certain degree of accuracy? Should we use a 4th degree polynomial, or would a 3rd degree polynomial work? Okay. And to answer the questions, we have to look at the absolute value of the remainder. So the remainder is the difference between the function and the 10th degree and the nth degree Taylor polynomial. That's called your remainder. That's your error, okay, in your approximation to the function at the x value you're looking at. Now, to get a bound on what this remainder is, we use what's called Taylor's inequality. Taylor's inequality. And Taylor's inequality is given in the formula sheet in your course content under section 8.7 that you can download that that handout. So this is the Taylor inequality right here. The absolute value of the remainder is less than or equal to m over n plus 1 factorial times x minus a to the n plus first power, where the value of m is determined by finding the largest value of the n plus first derivative over at your x value. Okay, so this can be proven. Actually, this result can be proven. We're not going to go through the proof, but they talk about it in the book. Actually, in section 8.7, they talk about it. And I'm trying to look here. Remember back in section 5.9. Remember section 5.9 when you were looking at approximate. You were approximating integrals with like the trapezoidal rule, the midpoint rule, and Simpson's rule. Remember you had error. Remember how many remember the error-bound formulas that you saw for those rules, trapezoidal rule, midpoint rule, and so forth in section 5.9? How many recall finding a value of m? Okay, so you could get an error bound on the approximation. I know it's been a while, but for who doesn't at least ring a bell? Okay, Cologne remembers. Thank you, Cologne. Michael remembers. Okay. And Snega remembers. Thank you. So this is really the same kind of thing. You have a bound on your error given by m over n plus 1 factorial times the absolute value of x minus a to the n plus first power. So m is the hard part, finding that value of m. But this is what we're going to be talking about. And what I'm going to do is I'm going to do example 1 with you. It's in the textbook, but I would like to do example 1 with you as a formal example that you copy down. But are there any questions so far? Okay, all right. So let me bring up this example. Okay, and let me give you a moment to copy it down. Okay, let me give you a moment to copy it down, this example, and then we'll work through it. use the approximation for the cube root of 7, like for example. So remember how I guess one way you can think about this as from the computer science perspective, think about your calculator. When you type in the cube root, say, of 7, let's say you type in the cube root of 7.9 on your calculator. You magically get an answer, right? Well, how many of you have wondered, gee, how does the calculator get that answer? I mean, how many of you are sort of curious about that? The calculator gives an answer for the cube root of 7.9. How does it get that answer? Okay, how many, do we have any computer science majors in here? Okay, Sine is, thank you, Sine. Felicity is, Gandhi. Okay, so, okay, well, this is, and Michael, yeah, I mean, how's the calculator get that? Well, there has to be some algorithm programmed in the calculator. I mean, the calculator, it's not like it's connected to the internet, right? There has to be an algorithm programmed in the calculator. So, and you know, mathematicians, you know, hundreds of years ago encountered the same like issues that you encounter. Hey, we need to compute the cube root of 7.9. You know, how are we going to find that? How are we going to approximate that? So this is going to show you how this would work. Now, let me ask you this. We're going to use a second degree Taylor polynomial about a equals 8. Why are they picking a equals 8? Why not pick like a equals 5? Why choose a equals 8? Why choose a equals 8? Why not choose like a equals 9? Well, 8 is between 7 and 9. That's right, Michael. But let's think about our function here. Our function is the cube root of x. Why is a equals 8 a nice value to expand our Taylor polynomial around? Why is a equals 8 a nice value? I mean, why didn't we use a equals 7? Okay, that's right. That's right. Thank you. It's a perfect cube. The cube root of 8 is 2. So when we write out our Taylor polynomials, we like to expand them about nice values so we can compute the function and its derivatives at the nice values. So first thing we're going to do is we're going to go ahead and get the second degree Taylor polynomial. To do that, okay, remember, and here's the formula for a Taylor series, but we're looking here at just a second degree Taylor polynomial. So that means we're going to be looking at just the first 3 terms. So that means I have to evaluate, well, I have f of a, my function is the cube root of x, but I need to find the first and second derivatives of the cube root of x as well in order to get the second degree Taylor polynomial T2. Okay, so let's go ahead and proceed here. Okay, so again, I'm finding the second degree Taylor polynomial about a equals 8. Okay, and I find, you know, my function is x to the 3rd power. That's the cube root of x. Here's the first derivative. Here's the second derivative of my function. And then I'm evaluating the function and the first two derivatives at a equals 8. Okay, so I mean, look it over, copy it down, look it over, let me know if you have any questions. I don't think I need to read this word by word. Okay, you're in Calculus 2, you know how to take derivatives. All right, let me know if you have any questions. I'll give you a moment to copy this. Okay. Now you notice that because we're expanding about a equals 8, computing the function and the first and second derivatives at a equals 8 is easy. And again, you know, we're trying to we're trying to get an approximation here of the cube root of x using a Taylor polynomial, and but the polynomial needs to be easy to compute. So naturally, I want the function and its derivatives, the values, to be easy to compute. So far, this is pretty basic. Now what we do is we construct the Taylor polynomial. Okay, well, the Taylor polynomial would be f of 8 plus f prime of 8 over 1 factorial plus times x minus 8. Remember, a equals 8. That's the value of a. Plus f double prime of 8 over 2 factorial times x minus 8 squared. So now what I do is I substitute in what f of 8 is, what f prime of 8 is, and what f double prime of 8 is. Substitute it in the second degree Taylor polynomial, and then now I have concrete coefficients. Okay. Let me know, please, if you have any questions. Okay, and then of course I'm gonna simplify things a little bit. This negative 2 over 288, that fraction. Hold on. I think I have. Let me see. Do I have an error here? One moment. One moment. No, I'm good. I'm good. I'm good. Negative 2 over 288 divided by 2 is the same as negative 2 over 288 times the reciprocal 1/2. That'll get you negative 1 over 288. So this is now my Taylor polynomial. Here it is. Okay. And so we say that the cube root of x is approximately equal to the second degree Taylor polynomial, which is 2 plus a 12th times x minus 8 minus 1 over 288 times x minus 8 squared. Now, it could be a very, depending on what your x value is, this could be a very bad approximation, right? The cube root of x could be approximated very badly by this second degree Taylor polynomial, depending on what the x value is. What value would the cube root of x and the second degree Taylor polynomial, what value of x would the cube root of x and the second degree Taylor polynomial be equal at? What value of x would t sub 2 equal the cube root of x? In other words, what I'm saying is my second degree Taylor polynomial will be equal to the cube root of x when x equals what value? So I'm looking for a number here. Does anyone want to make a guess? That's right, Colombe. Very good. Very good. If you substitute x equals 8, and in other words, what I'm saying is t sub 2 of 8 okay, and that's, putting 8 in for x, here. T sub 2 of 8 is just going to give you 2 because this term and this term will equal 0 when x is 8. So T sub 2 of 8, the second degree Taylor polynomial evaluated at x equals 8 will equal 2, and that is equal to the cube root of 8. Wow, why do you think that happened? Is that just a coincidence? Or why do you think that happened? I mean, it might make good sense that that happens. When we constructed the Taylor polynomial, what was our value of a? It was 8. Right. So, of course, the Taylor polynomial will equal the function at x equals 8. But not for the other x values. All right, so let me, are there any questions? Any questions at all? Okay, then let's move to the next page. Okay, so now we want to ask, how accurate is our approximation here? We're approximating the cubed root of x with that second degree Taylor polynomial about a equals 8. How accurate is the polynomial approximation of the cube root of x when x is between 7 and 9? Why would I have an interval from 7 to 9, by the way? Why am I picking that interval from 7 to 9? I mean, I could pick any interval, but why does it seem natural to pick an interval from like 7 to 9? Right, Kihindi, Kalom, and Tina. Yes, 8 is exactly between 7 and 9. 8 is exactly between 7 and 9. So, okay. We're going to use Taylor's inequality. Okay, we're going to use Taylor's inequality. And the inequality, again, in the handout, we are looking for a bound on the error between the second degree Taylor polynomial and the cube root of x. Well, that error bound is going to be m over 3 factorial, because 3 factorial is 2 plus 1 quantity factorial, times the absolute value of x minus 8, a is 8, to the third power. Third power because 2 plus 1 is 3. If you look in the formula, the power is n plus 1, right? The power. So what I'm doing here, let me just, maybe I'll go back to this page, but you know, this is what I'm looking at right here. This is what I'm using, Taylor's inequality. And I have n plus 1 factorial here, and I have that n plus 1 power. Okay, and we know n is 2. So that's how I'm getting this here. Now I'm going to find m. M has to be greater than or equal to the absolute value of the third derivative of at x. Again, let me go back to the formula. In the formula, m is greater than or equal to the n plus first derivative of x. Well, since n is 2, Rm would be greater than or equal to the absolute value of the third derivative of x. Okay, so that means then I have to compute the third derivative. I need to compute the third derivative of x. Now we know that the second derivative, of the cube root of x is negative 2/9 times x to the negative 5/3 power. So if you differentiate that second derivative, you get this third derivative. Okay. And you notice I don't round anything. I don't round any fractions. WebAssign's very picky about answers, so we don't want to round until the very end if we can help it. Are there any questions up to here? Okay, well then we are considering x between 7 and 9. That's the range of x values that we're interested in. Because our Taylor series is expanded around a equals 8, we know, I should say, because our Taylor polynomial is, its center of expansion is a equals 8, we know the polynomial will approximate the cube root of x reasonably well for x values near a equals 8. Okay, near 8. So between 7 and 9 is a reasonable range of x values. Okay, and so what I do is I study the absolute value here, the absolute value of the cube root of x. Well, that would be the absolute value of 10/27 times x to the negative 8/3. But since x is positive, x is between 7 and 9, x to the negative 8/3 is going to be positive. That's going to be positive. And so I can remove the absolute values. So the absolute value of the cube root of x is just 10/27 times x to the negative 8/3. And that's 10/27 times 1 over x to the 8/3. And that decreases with x. Okay, this third derivative, or I should say the absolute value of the third derivative, decreases with x. This here, 10/27 times 1 over x to the 8/3 power, is a decreasing function of x. Okay, it decreases with x. Well, and so now, Tina, we have to find m. We have to find m, and this piece of information is very important. Remember, m is by definition a value that's greater than or equal to the absolute value of your third derivative. Well, here's our third derivative. It decreases with x. So let me ask you, over this interval from 7 to 9, what would the largest value of the third derivative be? What would the largest value of the third derivative be? Over the interval from 7 to 9. Well, to find that, okay, I have to put in a number here. I have to put in a number, something to the 8/3 power. What number would go there? Well, we're not going to put in 8. I mean, I'm not saying we couldn't, but we wouldn't put in 8. We would put in 7. We would put in 7. That's right, Michael. That's right, Colombe. And why is that? Why is that? Because we would put in 7 here, because this function here decreases with x. It's a decreasing function. It's a decreasing function, right? You know decreasing function. I mean, you know, you have a x-axis here and a y-axis. Okay, and you have 7 and you have 9. Kind of drawing this quickly. All right, that's fine. And you have some decreasing function. Okay. Well, the function would take its highest value at x equals 7. And so that's why we put 7 in here. And then that's going to determine what your m value is. M will equal 10/27 times 1 over 7 to the 8/3 power. Okay, are there any questions on that? Please. So when you do this, when you find that value of m, you have to determine if your whatever derivative you're looking at, in this case it was the third derivative, the absolute value of the third derivative, is that increasing, is it decreasing? Because that's going to determine how you find your m value. And for your final exam, certainly if you give me an m value, okay, I need you to justify why you're picking that m value. You have to tell me about, you have to talk about your derivative, okay? Whether it's a third derivative or fourth derivative or whatever. Is the absolute value of that derivative increasing, decreasing? How are you justifying the value of m you're getting? And for the problems in WebAssign, for pretty much most all of them, it'll be pretty easy to get the m value. There will be one example where that I do have to talk about, but I'll talk about that example likely on Thursday, in Thursday's class. But are there any questions before we go to the next page? Okay. All right. So here's the value of m. And so, well, m is greater than or equal to 10/27 over 7 to the negative 8/3 power. So you're going to take m to be 10/27 times 7 to the negative 8/3 power. Okay. I mean, you don't want you want your m to be as small as possible because the m is going to help you determine your error bound. Okay, and you know we want to be as precise as we can be. So now we know what m is. Now we can work on finding our error bound. Okay. Okay, so here's the error bound right here. I've put in the m in the numerator. I have 3 factorial in the denominator. And now we have this, remember we had the absolute value of x minus 8 to the 3rd power. Okay, well we have to put something in for x. Okay, well the largest the absolute value of x minus 8 could get over the interval from 7 to 9 is going to be 1. So that portion of the error bound can't be any more than 1. And so you're going to get 10/20 for the error bound. You're going to have 10/27 times 7 to the negative 8/3 times 1 divided by 6, 3 factorial. 3 factorial 6. And so your error bound is going to be 0.00035, which is pretty good. It's pretty good. Are there any questions on that? All right, I'm going to ask you a question. Suppose that the range of x we're looking at is x is between 7 and 10. Let's just suppose. Okay, then what's the largest x minus 8 could get to be? In other words, what value of x would we put in here? Well, Kahindi's saying that the absolute value of x minus 8, the largest it could get would be 2. And why are you saying that, Kahindi? You're right. Because 10 minus 8. That's right, Kahindi. That's right, Tina. Okay, so, you know, it's not like meant to be hard, you know, finding the error bound. You know, we don't want any of this to be hard. So, I mean, you know, no matter what the interval is, you can easily find out, you know, the value of x in that interval that maximizes this portion of the error bound. And so we can say then that if x is between 7 and 9, our approximation, t sub 2 of x, will approximate the cube root of x. It'll be accurate to within 35 10,000ths. Okay. And, you know, that might be good enough for the work you're doing. For an astronomer, it probably would not be good enough, right? Because even little errors can throw off astronomy, right? Astronomical calculations can be thrown off by little errors, but if, you know, for maybe a simple application, it might be good enough. And that's, again, this is how mathematicians, you know, 200 years ago, this is how they, you know, well, they needed to know this information, and you need to know it too, as mathematicians and scientists and computer scientists. Now, what I've done here, by the way, is I've drawn. Well, I actually got this from example 1 in section 8.8. The figure 2 here, we've drawn the cube root of x, and we've drawn the second degree Taylor polynomial on the same screen. And the little dot up there, hold on, the little dot up there corresponds to the x value when x equals 8. So of course and you can see that the Taylor polynomial, second degree Taylor polynomial, approximate the cube root of x pretty well over a wide range of x values. Okay. Of course, the further away you move from the value of x equals 8, the worse the approximation will get. And you can see that, you know, you can see it get worse. And then in this figure here, figure 3, just a picture of the absolute value of the error is drawn. And again, when a equals 8, hold on here. Well, I'm just looking at, oh yeah, look, the interval goes from 7 to 9 here. I'm used to starting at 0, right? The x interval goes from 7 to 9. So right here at a equals 8, the approximation's perfect, right? But then as you move away from a equals 8, as you move, for x values like over here, and x values over here, naturally the error is going to increase, but it's still pretty good. The error doesn't get more than, 3 10,000s, right? So it's pretty good. How many think this is off, actually kind of cool? How many think this is pretty cool? Okay, some a little, maybe I have to do something to help you appreciate it more. Cologne says it's interesting. Okay. Okay. Tina says the work makes it not cool. Okay. And again, I trust everybody's in the class. I know you're not working on the exam because I deactivated it. I would do that even if we had a face-to-face class, right? Because I don't want students working on that or any assignments during the lecture. I want you to focus on the lecture, right? Okay, so let me show you how we can use this. Okay, what you have here, class, what you're learning, how many like cars? How many like muscle cars? Okay. How many like Corvettes and Porsches and I don't know what other muscle cars are out there, Ferraris. I thought I'd get a lot of responses on that question. All right, Tina likes it. Okay. Yeah, well, what you have here is a Corvette. What you've just learned, you've learned one of the most important, this is one of the most important problems you're going to see. Snega likes driving them too. All right, well, we're going to drive our little Corvette here. What's our Corvette? It's our second degree Taylor polynomial. I mean, here it is. Here it is. Let's use it. Let's try it out. Okay, let's use it to find the cube root of a number. Okay, let's try out our approximation and estimate the cube root of 8.24. I don't think any of you know offhand the cube root of 8.24. Okay, so how would mathematicians do this? How would they find this? Okay, how does your calculator find this? Okay, well, we have our second degree Taylor polynomial. X is going to equal now 8.24. That's your value of X. So the cube root of 8.24 is approximately t sub 2 of 8.24. What I'm doing is I put in 8.24 in for X. And think about what a computer can do, right? A computer, okay, like in terms of flop operations, what can it do? It can do adding, subtracting, multiplying, and dividing, right? Who can confirm that in the class? Computer science people who will confirm that's a mathematical computation is a flop. And is it not true that computers add, subtract, multiply, and divide? That's a mathematical flop. How many? Okay, Michael's heard of that. Kahindi has heard that. Okay. So everything I'm doing here, a computer can do. Okay. Now, I get down to here, and okay, 0.24 squared. Well, that's just 0.24 times 0.24. We can compute that. A computer can compute that. That's 0.0576. And then, okay, 0.24 divided by 12 is 0.02. And 0.0576 divided by 288 is 0.0002. That can be done. You learned that in middle school, how to take a decimal and divide it by a number. Okay, you learned that in middle school. Okay. And just so I'll show you, I'm just going to show you this next page. I'll come back to this, but here's the next page where I actually, and this will be on the recording, but I actually did all the computations needed to compute the second degree Taylor polynomial at x equals 8.24. I worked out all the necessary computations by hand, just like a mathematician, you know, several hundred years ago would have to do. Okay, just like a computer would have to do. Okay, so with those computations, and it's in the recording, it's there in the recording, you don't need to copy all that down. I'm going to get 2.0198. That's my approximation of the cube root of 8.24. 2.0198. Now, we're told that that answer should be accurate to within approximately 3/10,000ths. That's what we're told, right? Well, so we have faith that it should be a very good answer. If we compute the cube root of 8.24 on our calculator, we get 2.0198, 03268. So look, we had a pretty good approximation there. And I mean, the approximation is accurate to the 4th decimal place, right? It's accurate to the 4th decimal place. So our approximation is very good. I mean, naturally there are, you know, zeros here for the rest of the approximation, but our approximation is pretty good. Just with second degree Taylor polynomial, we approximated the cube root of 8.24 accurate to within 4 decimal places. And that's just with a second degree Taylor polynomial. If we used a higher degree polynomial, we'd do even better. Let me see, question on this, one moment. Tina asks, and this approximation works so long as x is between 7 and 9 because that was in our interval. Well, Tina, I did choose 8.24 because 8.24 is between 7 and 9. I have to have an interval, you know, about our A was equal to 8, right? So the interval is somewhere close to A equals 8. I know my Taylor polynomial approximation will do a reasonably good job near values of 8. So I picked 8.24. Okay. Now, what about if I wanted to do the, okay, you're welcome, you're welcome. What if I wanted to compute the cube root of 50? Would this second degree Taylor polynomial work well for approximating the cube root of 50? No, it definitely would not. Okay, so the point is too, you have to use the approximations for values of x that are close to that center point A. Okay, are there any questions at all on this example? Okay, let me stop the recording.